Well, let me just start off by saying that applause should not be for me, but it should be for Sean Cunningham, a student in our honors class who worked with us over the summer with 2 other students and produced that video. And he also produced, and if you've been to the Colloquium website, there's student-produced trailers. Sean also put those together, and they're really excellent. But welcome, and my name is Chris Roman, an assistant professor of oceanography in the Graduate School of Oceanography, and one of the co-coordinators of this year's honors colloquium. And on behalf of my fellow coordinators, Judith Swift, director of the Coastal Institute and professor in communication studies, and Peter Kernillan, professor of oceanography, welcome to this, the 6th lecture in our series investigating technologies and how they will change our lives from this day forward. So we're particularly excited about tonight's lecture for 2 reasons. First, nanotechnology. If you've been taking notes, you'll note that every one of our previous speakers mentioned nanotechnology. So it's a common denominator and an enabling technology in a lot of things. So we're very pleased to have a nice talk tonight, sort of laying out the basics of nanotechnology. And second, we're excited because we have an expert here at URI. So Professor Jason Dwyer is at URI, a leader in this field, and is going to certainly play a role in URI's part of the future related to nanotechnology. So this lecture series would not be possible without support from our major sponsors, including the G. Unger Vedelson Foundation, the URI Graduate School of Oceanography, and the URI Honors Program. And we also thank, as always, our sustaining sponsors behind me and Classroom Media Services, who keeps the lights on every week. And this lecture is also sponsored by the College of Arts and Sciences, Jason's home department. So for the basics this evening, please turn off your cell phones, any other devices you have, make any final seating or otherwise adjustments now. For reference, there's exits on each side of the stage, in the back of the room, and on the sides in the back. There's restrooms in the back, and if you go downstairs, there's restrooms on each side. At the conclusion of tonight's presentation, as always, we'll entertain questions, or the speaker will entertain questions. We ask you to submit short, concise, and if you're one of Jason's students, bone-crushingly difficult, hard questions. So you can do this 3 ways. You can send, or you can write your questions on some note cards, which have been passed around. Students will come around to collect them. They'll be taken forward and transcribed electronically. You can send a text message to 401-284-7444, or you can send an email to hcquestion@gmail.com. So send your questions in early and often to increase their chances of being read. And if you look down here and you don't see Peter's fingers smoking, you're not trying hard enough. So keep sending them in. And also put your name on the question so we know who you are. And just to note that we're not, I would say, filtering questions. We're just trying to combine common thoughts and make sure we cover a diversity of interests. And if you're at home watching via the internet, please send in questions. We're happy to know what you're thinking. And also I'll note that this evening's speaker is offered to entertain questions we don't get to after the fact and put those answers online. So they'll be posted on the Colloquium website. I think that's all I have. So on to the main event. So it's my pleasure to introduce Professor Jason Dwyer. And most of you know URI's tagline, think big, we do. Jason doesn't quite follow this, and he's more a person that's going, think small, he does. Right? So that's the way it goes in nanotechnology. So Jason got a PhD in physical chemistry from the University of Toronto in 2005, where he made a molecular movie camera to watch what molecules do during chemical reactions. So if you're curious, ask Jason. He continued this work in Berlin, Germany as a postdoc, where he was able to observe interactions between DNA and water molecules. In 2007, he worked in Vancouver, Canada, in biomedical diagnostics, and then later came to URI in 2009. He's the co-founder of Insight Nanofluidics, which is a nanotechnology company, and he's been published in Science magazine, including a cover article on the molecular movie making in Nature magazine, and has taken part or participated in Discovery Channel documentary Bullet Time. At URI, his research interests focus on nanofabrication devices that can sense and interact with individual molecules, and uses these devices in such areas as pharmaceutical testing and clinical diagnostics. So please welcome to the stage Professor Jason Dwyer.
Thank you, Chris, for that introduction. Thank you, Peter, Judith, and Chris for the invitation to talk about really small things. So to talk about nanotechnology. And I'd be a poor excuse for an academic if I didn't have a much longer title than this. And that title is Forging a Better Future, One Molecule at a Time. And so my thesis for this talk is essentially one that we can try to predict the future, or we can ask questions to try to guide what the future is going to be. And what I want to give you is my vision of nanotechnology and how we can use this as a force for better, to improve human health, to improve societal conditions. And so all of us know nanotechnology from daily life. I'm fortunate to just barely remember these days of having to carry around music on your shoulder. And there's a lot of people in the audience who've probably never seen something like this except here or in a museum. And instead, we've progressed to the point where there was this Walkman, which was hardly pocket-sized, and now we're to the point where we can carry massive amounts of data on tiny devices, and companies have gone so far as to name devices like these nano. And we'll see in a minute that that's not really nano, but the components of these devices are nano. And so the experience of nanotechnology in everyday life is really one that can be summarized by the sort of Olympic motto of nanotechnology, which is faster, smaller, and cheaper. And I want to go beyond this motto in this talk tonight to talk about what nanotechnology can do to go beyond faster, smaller, and cheaper to really make a difference in the future. To how nanotechnologists, how everyone in this audience, users of nanotechnology and crafters of public policy that govern nanotechnology, can bring everything together in the future. So the fundamental definition of nanotechnology from the point of view of a nanotechnologist is really one of length scale. How big is a nanotechnological object? And nanotechnology takes place using Lego bricks or components that are on the length scale of 1 to 100 nanometers, where 1 nanometer is a billionth of a meter, which is about the same size of government that the Tea Party is looking for, just to put things in. So it's really small things. And what can we do with those small things? How small is a billionth of a meter, really? And so we can look at everyday objects like a baseball, 10 million nanometers. So that's definitely not nanoscale. We can go smaller and remember back to high school biology and think about red blood cells. So these are the objects the objects that carry oxygen throughout the body to where it's needed. And these are still not nanoscale because they're about 10,000 nanometers in size. So we have to go smaller still. We can go to the length scale of a virus, and now we're talking 100 nanometers. Still smaller. What's smaller than a virus? Well, we can start to look at a protein like this antibody that's about 10 nanometers in size. And we can go still smaller than that by asking a more fundamental question that what is it really that delivers oxygen in the body? And it's actually a molecule called hemoglobin that's about 5 nanometers in size. Now, this is a particular representation of this molecule, which to me and to the chemists and physicists in the audience is probably a beautiful representation of this molecule. But it's a very limited representation of what this molecule actually is. This is a much more accurate definition of what the molecule hemoglobin does. This is a more accurate description of the molecular machine that is responsible for carrying oxygen from where you breathe it in to where it's needed in the body. It's 5 nanometers in size, and it has moving parts. And we're full of molecular machines like this. If you're sighted, every time a photon of light comes in, there's a molecule that goes like from this to this. There's a mechanical motion that is the first step of vision. And so the body is full of magnificent machines that operate with moving parts on the molecular scale. And these moving parts are made up of atoms and molecules themselves. And so this is really where a nanotechnologist wants to be, on the length scale of viruses and of molecules. This is where we want to work. These are the Lego bricks that we want to make devices out of. Now, it sometimes is useful to take a step back and again say, all right, well, what does that really mean? So if I'm a builder of cars, I might find it convenient to build a scale model of a car. And that scale model is going to be much smaller than the car so that I can pick it up, I can turn it around, I can look at it from different angles. And if I'm a builder of a house, I might find it convenient, it's not a bad house, to make a scale model of a house. And so as a chemist or a nanotechnologist, I do exactly the same thing. I build a scale model of a molecule. The difference is, this is over 1 million times bigger than the actual object that it represents. So if we're builders, we can't use these tricks of making something smaller to make it easier to work with. If we're building using molecules, we have to make our models to be much bigger. And so when it actually comes time to take what we can learn by looking at this molecule and build the actual component, then we need much, much smaller tools. And we need to come up with new tricks so that we can manipulate matter that's on the 1 to 100 nanometer length scale. So my first introduction to nanotechnology was to this particular molecule called Buckyball. It's made up of purely carbon atoms, C60, and you may notice a striking resemblance to a soccer ball. So this is a nanoscale soccer ball, and this was discovered in 1985. The Nobel Prize was given in 1996 for its discovery, and one of the winners was rather appropriately named Professor Smalley. Someone must have known. Now, this thing, at that point, was just a really small object, and at that point in my chemical education, I thought that was pretty neat. But as I went along in chemistry, I started to think, well, maybe this could be used as a container for another molecule, so a molecular briefcase, if you will. So this is what nanotechnologists do. We're the ultimate recyclers. We try to take small objects, and because they're often so hard to make, we try to squeeze as much purpose as we can out of them. And so, but we can think far beyond this. This is a very simple passive element. So how do we try to step towards this molecular machine that carries oxygen within the body for us? So we can start to think about things like DNA robots. So this was actually built in 2004, and it's a DNA walker. And there are a number of critical things to think about this. So what you might imagine, if you believe me that this could be used as a molecular bottle, well, put arms on the DNA walker, give him this bottle, and ask him to deliver drugs to a particular part in the body. This is like giving me a medicine bottle, dropping me in Narragansett Bay, and asking me to deliver medication to someone in Portugal. So as soon as I step off the beach, I'm going to be buffeted by waves. So there are going to be massive forces that are going to be at play that are going to prevent me from finding my way. And so this is why this DNA walker has to have something to walk on. So if you imagine that this is some sort of stream that it has to cross, they've put in particular stones so that this DNA walker walks from one stone to the next and to the next. So this is not a freely walking DNA that you can let him loose in the body and he will go exactly where he needs to be. He'll end up washed up on some shore. So you have to give him anchor points to step on, and you also have to give him a path to follow. So these are some of the challenges when you build something so small. You have to take into account that right now I'm standing here and I'm being subjected to massive numbers of collisions with molecules. And I'm okay because I'm kind of big. But here, this thing is so small, it's the same size as the molecule. So when they go colliding into it, it's going to get washed in one direction and then the next, just like I would if I were to be dropped in Narragansett Bay. So there are the dreams of nanotechnology, and then there are the realities of nanotechnology, and we start with dreams, and we try to make them happen. And so I want to talk today about the tricks that we use in order to make those dreams come to fruition. So it also requires us to think about things in often different ways. This is another popular building block of nanotechnology called a carbon nanotube. So it's a rolled-up sheet of carbon. It has amazing electronic and mechanical properties. I look at this, and I, of course, see a nanoscale test tube because I'm a chemist, and that's how I think. But you can do a lot of other things with this. When I was in Kyoto earlier this year, I saw an exhibit where they showed a rope that was made of human hair, because when they were building the temples, the ropes of the day did not have sufficient mechanical strength to hoist the massive beams that were constructing the temple. And so we can imagine if they can turn fibers like hair into materials, we can also turn these carbon nanotubes with their incredible mechanical properties into building materials. And so people have talked about using these as ropes for elevators into space. But we can also think about this in another way, that if we pour concrete and we want to build a wall, we will reinforce that wall with rebar. Well, nanotubes can serve as nanoscale rebar to make materials stronger and lighter. And so a lot of what one's trying to do, yes, we want to make molecular scale machines, but we can also take advantage of the fundamental properties of materials, their strength, their electronic properties. People are trying to turn these into the active elements of high-definition televisions. So if you can imagine this nanotube, it's about a nanometer across, that's pretty high definition. So there are a lot of applications that you can do, that you can come up with when your components are so small. What you can also do is to take this nanotube, and if you had some way of cutting it open and unrolling it, then you would have the new wonder material of nanotechnology, which is a sheet of carbon, a single atom thick called graphene, which has amazing mechanical and electronic properties. So you can start to think about making materials out of this that are stronger and lighter than other materials. You can put this into electronic circuits to make them run differently, to get new performance out of those circuits. Now, I don't know about you, but every time I go into the kitchen and I unroll saran wrap, which is about a lot more than 100 nanometers thick, I end up with it wrinkled and kind of stuck together. And graphene works in exactly the same way, that it's often difficult to make sure that you get it flat. So we have this idealized picture of what it could look like. This is our dream of what graphene could do. And very often we have to deal with the wrinkled reality of graphene. And so how is it that if I have trouble in the kitchen with this thin film of saran wrap that's many more nanometers thick than graphene, what do we have to do when we get graphene? We have to come up with different tools. And we have to come up with new ways of looking at things, and we have to make a lot of mistakes so that we can figure out how best to do it. So I want to give you one of the major approaches to nanofabrication. How do you make these tiny objects? So all of you with cell phones, laptop computers, how is that made? So if we want to dream about what we can do with nanotechnology, we have to know what the physical limitations are, but we also have to know, how do people make these objects? And so the semiconductor, the chip in your computer or your cell phone, is made through a process called top-down nanofabrication. You start with a piece of silicon. You deposit a thin film, and that thin film could be gold. How do you get a thin film of gold? You take a chunk of gold, you boil it, the atoms come up, you allow them to condense onto the surface of the silicon, and you stop when you have a film that's between 1 and 100 nanometers thick. You can also introduce gases to come and react over top of the silicon and stop again when you have a film that's 1 to 100 nanometers thick. So that's the starting point of all top-down nanofabrication, is to deposit a thin film. Then we need to turn that thin film into something. We need to sculpt it. So top-down nanofabrication is really a process of sculpting. We start with more material than we want, and we remove it from places that we don't want it. So how do we do that? We deposit something called a photoresist, which is not much more than photographic film, which is, again, losing its strength as an analogy with a lot of my students. It's a photosensitive plastic that when you expose it to light will chemically change. So we bring in a stencil, which is called a mask in the trade. And the stencil, or the mask, has open spots where light will be able to come through and blank spots where no light will be able to come through. So the next step is to take advantage of the photosensitivity of the photoresist. So we shine a light on it, and we chemically change the photoresist wherever it was exposed to light. So now we've put features in the photoresist, still not in the thin film where we want them. So we take away the light, we take away the mask, but we're still left with this film of photoresist, which we need to wash away with a solvent. So this is like if you have nail polish, you want to take it off with nail polish remover, only you do it in a particular pattern, only where the light had hit it. And so now you have a pattern photoresist, still not a pattern thin film. You need to come in with something like reactive ions, so gases that you've made particularly reactive, and they'll start to eat away at the thin film wherever it's not protected by the photoresist, and if you wait long enough, it eats it away entirely. So now you finally have that pattern-thin film. After all of that, you have your masterpiece, your final sculpture. So you strip away the photoresist, and you're left with the thin film. So it's a long process. And it starts with a nanofabrication facility, a building. So this top-down nanofabrication, the stuff that makes your computer, your cell phone, is big science, big technology, big budget. So you really can't do much by way of high technology advances these days without sophisticated infrastructure. And so I want to step away from the talk for a moment to again thank the people of Rhode Island for having voted to give URI a new chemistry building, because it will allow us to do some of the things that I talk about here. But a nanofabrication facility, this one's at Cornell, and it's a national facility because you have to add about one more zero to the price tag of a typical building. And the reason is you need inside something called a clean room. Now, nanofabrication is probably one of the few lines of work where you have to wear what look like your pajamas to work. And the reason is that when you try to make nanoscale objects, even something as small as a speck of dust is an incredibly huge object. One speck of dust in your device, and you're finished. You might as well go home at the end of the day. So I'm constantly shedding fibers off of my jacket, off of my face, and so you want to protect your devices against that. Even the paper that you take into a clean room of a nanofabrication facility is a special type of paper that resists flaking so that you don't get fibers coming up. Once you have this, and once you have the skilled people that know how to do this process, you need to fill that building with something. And so more zeros come onto the price tag because you need, for every single step that I showed you of that top-down fabrication, you need another piece of equipment to do it. But once you've put the investment into it, once you've mastered depositing these films and sculpting them away where you want to sculpt them away, then you can do a lot of things. One of the first things that nanotechnologists do is to make the world's smallest business card. It makes the people who pay your paycheck a little bit happier, usually. Now, my own company uses top-down nanofabrication to make what we bill as, no surprise, the test tube for the nano age. But it's really more of an aquarium, that we can take cells and we can take molecules and we can observe them in their living environment, which is typically underwater. And we can do that using methods and ways that no one else has, that you can't by any other means. And so nanotechnology truly is an enabling technology, that it allows other scientists to take tools and to do experiments and to perform investigations that they couldn't otherwise do. And of course, the ultimate, faster computers. So far I've talked about how things are smaller. And that's a pretty Spartan representation of what nanotechnology is all about. So for a nanotechnologist, the starting point is the size. But what becomes really interesting is that when you shrink matter down to the 1 to 100 nanometer length scale, you start to get size-dependent properties that emerge. So we've been doing nanofabrications as humans for a very long time. The red in the stained glass windows of the great cathedrals of Europe is particles of gold. Now, this is an alchemist's nightmare, that as you take gold and you shrink it down in size, it appears not to be gold anymore. Now, it's still chemically gold, but the color has changed. And nanotechnologists have a much more deterministic control over this these days, that we can actually make gold nanoparticles, and we can change the size of the gold nanoparticles from 5 to 10 to 50 nanometers. And as we do that, we can change their color. So we can tune the properties of these particles by changing their size and nothing more. Now, it's not just gold that does it. Semiconductor particles like cadmium selenide will do this. So this is a general phenomenon that we can take advantage of. So what can one do when one has control over the size of matter on that scale, when one has the ability to tune properties? Well, we can take these things, they each absorb at a different wavelength of light, and we can start to put nanoparticles into solar cells so that we can more efficiently harvest energy, so that we can tune how the energy comes in and where it goes and how we use it. And so in applications of green energy, nanoparticles have a starring role. One of the names of nanoparticles are artificial atoms. And so nanotechnologists are very good at mastering these, at tuning them. This is how nature does it. So this is the light harvesting antenna of a higher plant. It's a beautiful, beautiful molecular system. This is how bacteria harvest light. And so what nanotechnologists are interested in doing is taking what we've learned about artificial atoms and can we make these structures that nature makes already? Can we harness them somehow? Can we make a device where this can be plunked down and harness energy for us more easily? Now, nanoparticles have a strong application in medicine in a number of roles. One of the challenges of drug delivery is that if I'm not feeling well and I pop a pill, then there's a long journey for that drug molecule from the point where I swallow it to where it needs to get to where it gets to where it needs to be in the body. And there are numerous barriers for that drug to get there. So at those barriers, it's like if I decided to go out to a really exclusive club. So I put on my jacket, I make sure my hair looks short. And I get up to the door and I meet the doorman, and he looks at me and he says, "Back of the line." And that's what often happens to a drug that doesn't quite have the right properties to make it past that barrier. What I should have done is called up my much cooler older brother and said, "Can you come?" We get to the door, he puts his arm around me, and the doorman says, "Okay, you two can go in." So I'm taking advantage of this chaperoning property of my cooler older brother, and we can do the same thing with nanotechnology, that we can cause a drug to couple to a nanoparticle. We can either entirely wrap it in a shell, or we can have it sort of tagged onto the outside. And remember, we have control over the size and the properties of this nanoparticle, so that we can get this drug molecule into the cell. So nanoparticles have a tremendous application in therapeutics. They also have a strong application in imaging. So gold nanoparticles, they're pretty shiny. And you can design them so that they can recognize markers on the surfaces of tumor cells, for instance, that aren't on the surface of normal cells. And so that if you see this shiny particle on the surface of a cell, you can say, that is a tumor cell. You can let the nanoparticle essentially light up this cell that you want to detect. But you can go beyond that, and you can make the nanoparticle the active therapeutic itself. You can take nanoparticles, and if you inject them or cause them to aggregate in a tumor, you can have tuned those nanoparticles so that they absorb light of a particular wavelength, and you can use a light source to essentially locally heat up the nanoparticles inside the tumor and cook the tumor. So the nanoparticles themselves, by being able to tune the properties of that nanoparticle, you can tune its therapeutic value. So all of these things, how do they come together? Nanotechnology is fundamentally interdisciplinary science. Kay Park in mechanical engineering is a nanotechnologist. David Worthen in biomedical and pharmaceutical sciences is a nanotechnologist. Vinka Craver in civil and environmental engineering, also a nanotechnologist. Peng Wang in chemical engineering, nanotechnologist. Radha Narayanan in chemistry is a nanotechnologist. Mindy Levine in chemistry is a nanotechnologist. So there are people across this campus, and this is only a very small representation of the nanotechnologists here at URI and here in Rhode Island. But they're from all sorts of different disciplines: fundamental science, engineering. We have nanotechnologists in physics, in biology. So you need people in all of these disciplines to make these applications happen. Now, for those of you who are scientists, you will notice that, yes, I have indeed recognized chemistry in its rightful place as the central science. And the reason is that when we want to modify things on the molecular scale, chemists have been doing that for a very, very long time. We just thought it was chemistry. And so if you're going to call it nanotechnology, we're willing to go along with it. But we can craft these nanofabricated structures. So when we look at things, we're fundamentally seeing things as molecules or collections of molecules. That's what the chemist does. So this is sort of one of my favorite cartoons that essentially we have a lot of different ways of solving problems. So here's Caveman. He has the answer, of course. I used to be like that in high school. Ooh, ooh. Gets up, solves the problem, and what happens? His kid says, "Thanks, Dad, that's really relevant." That's the way we used to do things. So nanotechnology moves incredibly quickly, and the Stone Age of nanotechnology often feels like it's last week. And so how is it that we move forward in nanotechnology? How is it that we make advances? And so the one thing that I've really given short shrift to so far is nanoscience. So nanoscience is the underpinning of nanotechnology. It discovers the ways to do things. So a real definition of nanotechnology is not things that are on the 1 to 100 nanometer length scale. That's a starting point. But the real definition is, or closer to the real definition, is one where understanding and controlling matter at the nanoscale leads to unique phenomena that enable novel applications. This is really what the nanotechnologist does. We don't just want small things. We want small things that do different things, that work differently, that we can harness things in different ways. And so this understanding and unique phenomena is really the dominion of science. And as I was putting this talk together, it reminded me of a science show that I used to watch back in Canada when I was young called Wonderstruck. Now, the host of this show was not a scientist, but he understood the scientific method perfectly. And he would begin every single one of these shows with the following introduction that I'm curious about everything, about why things are the way they are. Good science is good questions. So let's ask some good questions and see what kind of answers we get. So there are some people, I think, who seem to be in high school, surely all of us remember those days of learning about the scientific method and the hypothesis. I do that when I'm at work, but when I'm at home and I'm thinking about nanotechnology, I don't dream in hypotheses. I ask questions. I wonder, how does this work? Can I do that? And this is really what one can do in nanoscience. That if you've ever been in a nice place and you have that gecko running up the wall or across the ceiling, you can't sleep, and you look at it and you wonder, how does that thing run up the wall and across the ceiling? How does it stick to the wall but then peel its hand off and then move to the next position? This thing is a biological Post-it note. How does it do that? So it's not by glue. If you focus in on what this gecko's feet look like, if you zoom in, you see many, many small fibers, which act as a sort of mechanical glue. And you can describe the forces that determine the adhesiveness of this gecko, and you can be content that, all right, I now understand how that works. So that's the science part of this. The technology part of this is to say, I wonder what I could do with that. Well, what if I make the gecko's feet or a beetle's feet, what if I turn that into the adhesive for a bandage? And you could ask, why do you want to do that? Well, first of all, we've all had that moment where we have to decide fast or slow. So that's an interesting problem to solve, but I can go through life without having solved it. But it turns out that infant skin and the skin of the elderly is incredibly sensitive to the adhesive of standard bandages. So if you can do away with the adhesive so that you just have this mechanical adhesion instead of the glue that causes irritation, then you can have a much gentler bandage for use in medical care. But you can go beyond that because we're not limited. We often, as scientists, take inspiration from the way nature does things, from the way nature constructs things, but we're not limited to just how nature does it. So we can take this adhesive and we can put in an electrode so we can monitor the health of a wound. We can also put in a drug delivery system so that we can enhance the rate of healing if we so desire. So technology allows us to do a lot of things. Hook it up to your cell phone if you want, have remote monitoring of the wound. But this starts with the gecko scampering across your ceiling. And it starts with a question. So I want to move on to what I think is really the future of nanotechnology. Yes, we're going to get better at top-down nanofabrication. That's without a doubt. We're going to become more clever at how we do it. But there's something to learn from the way nature does things. Now, all of the students in the audience, I think, probably recognize this chair. I've moved enough in my life to have horrible memories of this thing. Comfortable chair, but when you get pieces. And you get this horrible little Allen key, and that's how you spend your weekend. What if you could design this chair so that the minute you open your box, it springs to life and assembles itself? Wouldn't that be great? And there are people, I think, in this audience who may go home tonight and figure out how to do this with bungee cords and springs. And if you do, I want to share the profits. But this is a fundamentally important thing. Can we get molecules to learn how to assemble themselves? So what is a protein? What is this antibody? The first line of defense of the body against invasion. It's a protein. What is a protein? A protein is a string of amino acids that have somehow folded into this incredible structure. Now, if a protein misfolds, then you get so-called famous mad cow disease. So this is a really important topic. So prion protein misfolded causes Creutzfeldt-Jakob disease. It's been implicated also in Alzheimer's, but that's a sort of an open question at this point. But once you have this structure, how does the antibody work? Well, an antibody finds a particular docking site on an antigen, the chemical invader, and it walks up to it and says, "Hello, antigen, I'm an antibody. I recognize you, and I'm not going to let go." So there is an assembly process that takes place, guided by the structure of the antibody and its unique energetics. Can we harness that sort of self-assembly to put our chair together or to put our nanoscale device together? So this talk is about the future. I think this is a strong part of the future development, is to make the molecules do the work. But this demonstration that I'm going to do also deals with a different sort of future of nanotechnology. That I've been a judge at the Rhode Island Science Fair since I got to Rhode Island. Last year, I started to walk past a student science fair project that I just couldn't walk past anymore. And so this is his project, only done much more crudely and not in as great a depth. So what I have here is a dish full of water, and I have a ping pong ball molecule. So you're going to have to suspend belief for a moment. This is my molecule that I'm going to have self-assemble. So I bring in my first molecule, and in comes the next one. So far, so good. I bring in the third. And so now you see this sort of pattern. These ping pong ball molecules are assembling into a triangle. And I can add the next, and they assemble into a square. You can see why I couldn't walk past this demonstration. And I can take it out, and they self-assemble back into a triangle again. And I add it again, and it goes back to a square. And if I push my luck, I can add 5, and I'll get a different pattern, and I'll take it away, and I'll get 4, and I'll get a different pattern. And I could, like Homer Simpson, do this all night long. But I won't. But can we do this on the molecular scale? Nature does it. So can we learn from how nature does it? Can we use this self-assembly or the ability of one molecule to recognize another molecule or another part of a molecule to do our assembly for us? So that really is the future of what we're trying to do with the self-assembly process. And so what I want to deal with is a particular application that interests me very much, and that is medical diagnosis and the impact of nanotechnology on medical diagnosis. So you go to the physician's office, what's the technology that you see? You see stethoscope, blood pressure cuff, reflex hammer. And in the right hands and with the right questions, this can tell you a lot about your state of health. But if there are more fundamental questions, what happens? You get sent off to another facility where they're going to do blood tests to look for the molecules that indicate your state of health. So you get another waiting room. But if you're a diabetic, you can sit at home and monitor your own blood sugar level. So one of the things that nanotechnologists are trying to work on incredibly hard is to make the detector of everything in your blood that could be bad for you device. And to do it cheaply and to do it reliably. And this is always the hard part, that there's a lot of things that I could do in my lab that work in my lab 70% of the time, which doesn't work well enough for the clinic. Or you need to sort of cough and tap the table and hope that the device will work. So this is where engineering comes in, to take what you do in your lab and to make it into a final device. So we get promising developments, we ask the right questions, we learn how things work, and then we have to optimize it to make it reliable so that it will actually give you the right answer when you need it. One of the things that I'm interested in doing in my lab is something called personalized medicine. And so the idea is that if you know someone's genetic information, you can understand their propensity for a disease. So there are particular places in the DNA that suggest a propensity for a particular disease, or in this case, can affect the rate at which a drug will affect you, so your rate of metabolism of a drug, or it can even determine that a particular drug just will not work for you at all. So the question is, can we get that information and use it in a reliable way for diagnosis? And so this is where technology comes in, so that instead of, can you do this by giving a drop of blood and having the DNA sequence analyzed? And what I'm particularly interested in is changes where all of us have essentially the same DNA bases all the way through, except for a change in a particular place. Okay? So that's the target. The tool that I use is something called a nanopore. Okay? So a nanopore device starts with a patch clamp amplifier, which is basically a pack of batteries and a current meter. Then I have salt water, a jar full of salt water, and in the middle of this jar of salt water I have something called a nanopore, which is a molecular scale hole. And what I do is I connect the battery and I get ions flowing back and forth, and that flow of ions is a current. And so all I do is monitor the current as a function of time. And so as long as the ions are going happily back and forth through that molecular-sized hole, then I know there's nothing else in the hole. But as soon as a molecule goes into that pore, it's going to block the flow of ions. I get a reduction in the current. And if I'm good, I can tell what that molecule is from the characteristics of that blockage. And by good, I mean really good. It's like trying to figure out what you had for dinner by unscrewing the drain of your kitchen sink, putting your table scraps into the sink, running water, and trying to figure out by how much water is blocked what you ate for dinner. So it's hard, but what it allows me to do is to detect a single molecule. And so if you're interested in detecting diseases generally, you want to detect a tumor as soon as you can. So if tumors give off molecules that end up in the blood, you want to detect the first one that you can is when that tumor is still small. So single molecule detection is an important thing to be able to do. Now, how do I make these holes? Well, I can again borrow from nature. Bacterium Staphylococcus aureus secretes a particular pore molecule which likes to self-assemble in cell membranes. And so I buy this from a chemical company, I inject it, and it builds itself. But because I want to do more general applications, I'm more interested in making my own nanopores, which I do by something called top-down nanofabrication. Okay? The way I do it is I take an electron microscope and I turn it into a drill. So instead of using the electron microscope to image, I use it to shoot holes in a membrane, a thin membrane, and I can get holes that are as small as 1 or 2 nanometers in size. And if I keep shooting electrons at this membrane, I get bigger holes. So the question is, to do personalized medicine, we'll get back to the nanopore in a middle, what I'm interested in doing is telling the difference between 2 strands of DNA that differ in a single place only. So a single letter of the DNA code is changed between these 2 strands of DNA. How do I tell the difference between these two? Well, I ask a different question, because I want the molecules to do the work for me. So we all know this famous double helix structure of DNA. So DNA forms that structure because DNA molecules can recognize other DNA molecules, just like the antibody recognizes the antigen. And so I'm going to use this strand of DNA to recognize this unknown strand of DNA. So I bring it in, and it forms a double helix because every single one of the hands of the DNA molecule is shaking a hand on the other side. So now I ask, well, what about this other strand of DNA? So I bring in the same hands of DNA, the same sequence, and I bond it to this one. I let it recognize, and right in the middle, it doesn't recognize. So there's a missing bond. So now I have a duplex that's held together by one less bond than that. How do I tell the difference between these things? I pull them apart, and I measure how long it takes. So now the question is, how do I pull apart a strand of DNA? And that's where the nanopore comes in. So the experiment that I'm going to do is I'm going to start with a piece of DNA that will recognize another piece of DNA. And I build some other molecules onto it so that I can go ice fishing with it. Okay? So this thing is my DNA hook and bait, and it's going to recognize another piece of DNA. So what do? I take a pore molecule, this is me on the other side, wondering what fish are underneath. And I have my fishing line, and I connect my battery. I get a drop in current. That means that my hook is through the line, is through the hole. And then I wait for the fish to bite. And at some point, the DNA is going to recognize, or it's going to get a bite. Okay. So now what do? I want to measure how long it takes to pull this thing apart. So here's where the wonder of nanotechnology really takes over. I'm going to reverse the hookup of the battery so that it pulls this thing back up. This pore molecule is an amazing thing in that it's wide enough to allow single-stranded DNA to go through, but too narrow to allow double-stranded DNA. So that as I keep pulling, yes, I turn into the worst fisherman ever because I lose every single fish that I catch. But as I pull this up, I'm going to break apart this duplex. And so all I do is I time how long it takes to pull it apart, because that will tell me how well this DNA has recognized another strand of DNA. So what do I need to do? I need a battery, I need a current meter, I need salt water, I need a hole, I need DNA, and I need a stopwatch. And with this, and a whole lot of other stuff that I don't have time to talk about, we can start to think about personalized, or a tool for personalized medicine. But this is where all the difficulty comes in, that how do you put all of this together? So that's the technical side of things. It's fundamentally interdisciplinary work. So this technique was really pioneered at the University of British Columbia, where I was fortunate to spend about 2 years learning how to go molecular ice fishing appropriately in Canada. It's now being taken up by my students here at URI, where we're moving from this self-assembling molecule to synthetic pores that we can make ourselves, that we can make more easily into electronic devices. So some of you who are here in the balcony especially may have some of these students as your TAs. What are they doing in the lab? So what they're fundamentally doing is creating the next generation of textbooks. They're finding the knowledge to write the next set of textbooks, and in the process to try to make better technology. And this is, of course, where we turn our slides, always as academics, into NASCARs with a bunch of labels on it, but we've been fortunate to have funding for this project by the National Institutes of Health, by the Rhode Island Foundation, and the Rhode Island Consortium for Nanoscience and Nanotechnology. And this is an umbrella group right now to share equipment and expertise within Rhode Island between URI and Brown so that we can much more easily leverage the existing tools that we have. So we finally come to this famous logo, which when we from URI as nanotechnologists go to conference, we get some ribbing. But it really is true in the sense of what I, as a nanotechnologist, and all of the nanotechnologists that I know are trying to do. We really are trying to think big. We may have small tools to do it, but what we're really trying to do is to solve human-scale problems and global problems. So this truly is a relevant motto for us as nanotechnologists. So in terms of the future of nanotechnology, it's interdisciplinary and has to become increasingly interdisciplinary. So I've talked to you about clinical diagnostics. the typical Western operating theater. What about this? Can we create tools that can be useful in Haiti, in a makeshift clinic? So can we create tools that can diagnose malaria or tuberculosis far from clinical conditions? And so my inspiration in this is really this photograph, and for a couple of reasons. The first is that these two baby girls were born to mothers with HIV, but are themselves free of HIV. And that's due to a combination of research and education, mostly carried out by the Gaia Vaccine Foundation. And so when we think big, we're really thinking human scale and global scale. So can we build the technology? Can we ask the questions that allow us to build technology that works equally well in this operating theater as in that one? The other reason that this is a personal inspiration to me is that this is my wife, who is herself an interdisciplinary research center. PhD in synthetic organic chemistry, so she's one of those early nanotechnologists who's really good at making complicated molecules. Spent some period of time trying to synthesize anti-malarial candidates, and then moved on to do a master's of public health. And the reason is that the questions that she was interested in asking really went beyond pure chemistry and had to deal with how people interact with devices, how regulatory environments affect which devices we make, which drugs we develop. And so her particular approach was to take her technical background, where she could talk to synthetic organic chemists, and say, look, maybe we need to ask questions to go in this direction. So this is what's exciting about the Honors Colloquium, is that we have people here from a variety of backgrounds who are all talking about the future. And they're at this amazing stage of their lives where they can take whatever courses they want at university. They can do whatever they want. They're free to ask questions. And so the questions I would ask you to ask are questions of significance. What can we do? So if you're a business major, can you start a business that can put diagnostics into this environment? If you're a philosophy major, can you ask questions about the ethics of making nanofabricated devices and implanting them in the brain? So everyone has a contribution to make to this. And I think we're at the point where we really do need, when we think of everything that we do, everything is becoming increasingly connected. Everyone knows how to use a device. But can you think about how to create new devices that do different things and can use them in different applications? What can we use this technology for so that instead of greater convenience, faster, smaller, cheaper, we can think of better technology? So with that, I say we do indeed try to think big. Thank you.
Okay, we'll move on to our questions. And if you were writing questions and have them on a card, please pass them to the aisles. This is the time to do that, and we'll have some students collect them.
And what's interesting to me is at last week's talk, Judith, you made the comment that pencils are an old technology. Well, the graphite in pencils is actually the basis of carbon nanotubes, Buckyballs, and in particular graphene. So it's a nice parallel, I think.
Okay, well, since we're talking about that, we'll start off with our first question from Natasha Nemeth. So what are the more plausible macro-scale applications other than elevators into space, which she'd also like you to comment on, for carbon nanotubes, and when can we expect them in the future?
So I think that right now what seem to be the most promising applications are as electrical components and as components to enhance the mechanical properties of materials. So, I remember when I was in Toronto, there were people in the forestry department who were trying to take cellulose fibers from trees and put them in plastics, the great Canadian export of unprocessed trees, essentially, to make them lighter and stronger. And you can do the same sort of thing with nanotubes. So I think it's really enhanced electrical and material properties for carbon nanotubes.
Okay. what will the influence of nanotechnology be on fashion?
Right, okay.
I just read them.
Right, so, no, but so one thing that I had never realized before I got to URI, so I knew that there was a textile department, but I didn't know that within the textile department there was a guy who was making dressings that actually have components that can be used to promote healing of wounds. So this sort of vision that I showed you of this gecko foot bandage is really something that is being done already here. One of the things that strikes me as sort of interesting is, so I have this shirt. If we go back to the overhead projector for a minute, please. This has always struck me as sort of disturbing in some way. So it's one of these stain-free shirts. And if I drop some water on it, it's really kind of disturbing on the one hand, but this is, I'm not a duck, and I'm not wearing a duck skin. But this is the sort of thing that you can do with so it's, maybe it's not so much fashion as attire, but you know, you can do things like put in fibers that, as you walk, recover energy from your gait, so you can power your own devices. If you want, you can make your clothes shiny with gold nanoparticles, but I think, and really, it's lower cost at that point because you just need so few of them. But I think, you know, my view of this is really one where my interest is really on what we can do in the health field. And energy as well. It's not my particular area, but this is really where I think most of the applications can be. But, yeah, maybe if I'd worn a nanoparticle shirt, I could have gotten into that club.
Okay. Question here about nanotechnology that relates to energy. And it says, if we can harness the energy within a protein assembly, then what else can we do in life with that type of power? And how would it relate to nanotechnologies?
Right. So I think if this question is dealing with the light harvesting antenna, and it's essentially, this is what you would want to be able to do. So everyone who's talking about energy, how we can turn biomass into fuel, so you take the energy of the plant, or energy of the sun, you convert it into a plant through this light harvesting complex, and then you have to process it to get whatever fuel you want. And if you could actually directly take the leaf of the plant and plug it into your iPod and walk around, it's really the equivalent of what we want to do with nanotechnology, is to create an artificial leaf that is sufficiently efficient so that it can power your devices. So I think, you know, as long as the sun's shining, or you can store the energy in batteries. And so nanotechnology also has applications in energy storage within batteries, not just conversion, but storage. Then it's free energy, basically.
Okay. Can you isolate the flu virus and attack it with a nanovirus?
So what you saw in last week's talk was something called bacteriophage, which after he talked about it, I didn't want to talk, or I didn't think it was quite right to talk about it anymore, but it's a virus that attacks a bacterium. And it looks like a lunar lander, and it comes down, it recognizes chemicals on the outside of the bacterium, it comes down, and it fires DNA into the bacterium, and it can lead to lysis. And so I don't see any principle that would prevent us from constructing a similar sort of object that will attack a virus in that way, that will recognize some molecular characteristics on the surface of the virus and allow us to attack it. So really, the reason that I talked about self-assembly and molecular recognition is that this is really a general scheme of operation. And so you now have this sort of basic understanding of how we can do things. You can do it top-down, or you can let nature do the self-assembly for you, and then you can start to think about the applications that you can use those for. So, yeah, I don't see a limitation to doing that. I don't know how to do it, though.
Can can you give a very specific example of something you think we'll see in the next 5 years related to nanotechnology that will have a big, and the person wrote capital B-I-G, impact?
I think it comes to this issue of, so when I talked about thinking big and people in business, what kind of business can you think about? This is something that's really coming now that you get a lot of nanotechnologists talking about what we can do with technology. So this is a pH meter, but you may remember pH paper that changes color depending on the acidity of the solution. So this is a glucose meter. What can replace it? Glucose paper. And so there's a company called Diagnostics for All that's a spin-off from a very prominent nanotechnologist at Harvard. The company's called Diagnostics for All. And essentially what they're trying to do is to use nanofabrication to create diagnostic devices out of paper so that a single diagnostic device will be cheaper than a postage stamp. And it's much more sophisticated than, of course, regular pH paper, that you have different reaction chambers. But all of the principles of nanofabrication work on this sort of application. So you dip it in urine, you get some color change that's characteristic. How characteristic? You take a picture with your cell phone, transfer that message back to the Capitol, and then you have diagnosis. And so this is an area where I think this reality of thinking big is something that nanotechnologists are really trying to do. But it's something that requires everyone, in the sense that there's a particular model for this company that you need to put into place in order to be able to afford to do this. Right? This is not, you can't charge $100 per diagnostic if you want to put it into general use globally. But this is really where nanotechnology can make a difference. So I was talking to a student at dinner who had done some clinical work in Ecuador where people were doing diagnostic tests with the same sort of glassware that my first-year students have here at URI. And so this is, when you're trying to diagnose something as difficult as malaria or tuberculosis, you'd really like to be able to do it much better than you can do it with sort of stone knives and bearskins of the technology world.
Can you talk more about your micro camera?
About what?
The molecular camera, I guess, from your prior work?
Right, so the structure that I showed earlier, let's go to it. Right, so this one. So this structure that I showed is an X-ray crystal structure. So just like we would go to the physician and get an X-ray to show whether or not we have a bone broken, you can also get X-rays of a different sort to determine where in a molecule all of the atoms go. So this picture is one where you make a crystal of the molecules, you get the X-ray crystal pattern, and you can see what its structure is. And this goes back really, so why would one want to make a molecular movie camera in the first place? So when you write a chemical reaction, A, arrow, B, so reactant goes to product, that's the most boring representation of a chemical reaction that I could ever imagine coming up with in my life. And we have to, because there's so much going on in a chemical reaction. So as a chemist, when we look at that, we may think at the end, boom, or we may think color change. In my old field, what I thought, well, how does a molecule in vision, for instance, go from this to this? So anyone in chemistry, it's a cis-trans isomerization that starts it. How does it go from here to here? Does it go this way? Does it go this way? Does it go out and then come back around? So how does a chemical reaction really work? And so we took, instead of using X-rays to get structure, we used electrons. And what we did was, all of our reactions, we could start with light. So we would have some reaction. We'd say, go. And immediately, as soon as we would say go, we would take a picture with a really short pulse of electrons and get the structure at that instant. Then we would take a different part of the sample and we would say, go. And wait, 500 femtoseconds, so 500 millionths of a billionth of a second. run up and snap a picture using the electrons. Do it again. Go. Wait a little bit longer, 1,000 femtoseconds, and take another picture. And now you get this flip book of images of the structure evolving through time. And so to do it, you need about $1 million laser system, and you need to come up with some way of getting the electrons. But the electron gun is, again, technology is no friend. It's like a cathode ray television. You put your molecule in the electron beam, and you see the pattern on the screen. That's essentially, you get a particular pattern, and that tells you what the structure is. But you do this, it's like filming a movie. No actor would ever have worked for us. Because you record the movie one slow frame at a time. So start, record with a still camera, and the still camera is not fast enough to record the next frame, so then you have to reset, start over, and then capture the next frame and do it sequentially. And so with that, we were able to actually able to superheat aluminum to about twice its melting point, and it melted in about a millionth of a second, which is pretty fast.
All right. So Tony Atala was here a few weeks ago and talked about 3D printers. And so can you see nanofabrication essentially turning into 3D printing at a molecular scale?
Right. So here's the really interesting thing that you can imagine doing. So let's imagine it's in the cell phone. So you beam the synthesis instructions. So, all right. I work with DNA. How do I get my DNA? I phone up a company, and I say, give me DNA of these sequences. They have a set of machines that put the base pairs in order, link them together, and I'm done. And I don't really pay all that much money, and I get them back the next day. So that's how we synthesize DNA for use in the lab. So already this sort of design to order is there. Okay. So now imagine putting that in your cell phone, sending the synthesis instructions to the cell phone. You get some sequence of amino acids, and you've designed the sequence so that it folds up into the right shape that you want to give you the function that you want. So it's nice to dream about, and I think that that sort of thing can be done. The one thing that I want to say about that, though, is a few things you can never forget the reality of nanotechnology. If you're going to do that, you need a source of atoms, and you need a source of energy to do it. Right? This can never be forgotten. That if you want to go off to some remote area and synthesize something, you've got to have stuff with you and energy to do it. And that should be remembered. But yeah, in principle, I mean, we're at the point now where we can even start to design artificial antibodies. We mostly use them for detection, but they're out there.
Okay, so people are hanging in there. We'll try two more, I think. Do you think nanotechnology will enhance nature or replace it?
Well, that would imply replacing me, so I'm hoping that it doesn't replace nature. I think, no, I mean, I don't see that it would, I hope it would never replace nature. I think the problem is that in order to do that, you're plugging into such a complicated set of equilibria and interrelationships on so many levels between species, between plants. It's such a hard thing to do. But yeah, so I hope not.
Okay, so I guess our last question, someone's asking, so what are the downsides or the dangers in or in nanofabrication, nanotechnologies?
Right, so you know, we as humans have been, we're pretty good at coming up with weapons, unfortunately. And so sonic weapons, apparently. So you can imagine that you can, of course, use nanotechnology for less than good purposes. One of the things that, and so the uses of nanotechnology are something that people really do pay attention to, in the sense that what we're doing is we're plugging components into the length scale of nature. So if there's an active site in a protein or an enzyme that we're trying to block, and we design a nanoparticle that can block it, what we're doing is directly interacting with nature in a particular way. And so there is the fear that you can upset delicate chemical reactions by doing that. And so, in the medical regime, this is why people move incredibly slowly in nanofabrication, to think about what it is that you're doing. As you make things smaller, you're getting different properties, you're promoting different interactions, and we are always cautious of what it is that we're doing. But it's essentially anytime you create a drug molecule for a particular illness, you're trying to affect some process in the body. And so a lot of drugs turn out to be poisons. Right? So we can imagine the same sort of problem with nanoparticles, and yet all of us want that magic pill if we're sick. And so it's worth investigating, but it's worth investigating carefully.
Thanks. Okay. So thank you very much, and please be sure to join us next week, where we'll have a discussion on robotics for our oceans and our atmosphere, featuring James Bellingham from the Monterey Bay Aquatic Research Center, Joe Sioni from NOAA, and myself talking to you via telepresence from a ship near Italy. So thank you again, Jason.